Dear students, today I am giving notes on the last part of the first unit. Actually, we start with the definition that's of a closed subset of x2. That is, you are getting a function as a closed corresponding to it. How? Let x2 and yu be topological spaces. A function f from x to y is closed provided that if C is a closed subset of x2, then fc is a closed subset of yu. A remark is given, f inverse is continuous if and only if f is open, where f is a one-to-one function that maps one topological space onto another. And homeomorphism definition is given. Let x2 and yu be topological spaces. A bijection f from x to y is a homeomorphism provided that f and f inverse are continuous. Both f and f inverse are continuous means we are getting a homeomorphism. That is, we say x2 and yu are homeomorphic to each other, or y is said to be the homeomorphic image of x. And notice given, f from x2 to yu is a homeomorphism if f is both open and continuous. Then topological property is defined. What is a topological property? A property that possessed by a topological space X as well as every homeomorphic image of it. That is said to be a topological property. That is a property which is carried over by a topological space as well as every homeomorphic image of it. That is what we call as a topological property. We are going to study different topological properties in this section. Actually, topology is a study of topological properties of topological spaces. That's what the most important thing. And metrizability, we are going to prove that metrizability is a topological property. A theorem is given, the most important theorem. Metrizability is a topological property. We can go through the proof of it. Let XT be a metric space and YU, XD be a metric space and Y tau be a topological space. That's what taken. We have taken the function f from XD to Y tau. Take this as a homeomorphism. What we had to prove? We had to prove that y tau is metrizable. Define a row from y cross y to r. Metric row from y cross y to r by row of y1 y2 is equal to d of f inverse y1 f inverse y2 for y1 y2 and y. Clearly, row y1 y2 is greater than or equal to 0 if and only if d of f inverse y1 f inverse y2 equals 0. Also, row of y1 y2 is equal to row of y2 y1. That is, different conditions for the metric are satisfied here. And finally, we are taking the triangular inequality, that is for row y1 y2, that is what by definition d of f inverse y1 f inverse y2 which is less than or equal to d of f inverse y1 f inverse y3, that is one intermediate term is taken, plus d of f inverse y3 f inverse y2 is equal to row y1 y3 plus row y3 y2. Thus row satisfies all the conditions of a metric, that is row is a metric on y. Now we prove that the topology induced by rho is the same as tau. That's what we are going to prove. Or let tau1 be the topology induced by rho. We have to prove that tau equal to tau1. Let v in tau. That is, for that actually we have to prove that tau subset or equal to tau1. Similarly, tau1 subset or equal to tau2. Both we have to prove. So we consider v in tau and a point y in v. An element y in v and v in tau which is open. Then y equal to y can be written as f of x for some x in x. As f is continuous at x and v is a neighborhood of fx, there x is a neighborhood u of x such that f of u is subset or equal to v. That we have studied last class. But u is open with respect to the metric d. Therefore, the x is epsilon greater than 0 such that bd x epsilon is subset or equal to u. We claim that b rho y epsilon is subset or equal to v. It is an open board of the form b rho y epsilon. It is about y and with fixed radius epsilon that must be subset or equal to v. So you take an element here, let z be an element of b rho y epsilon, and that shows that a rho yz or a rho zy, that is less than epsilon, or a d of f inverse z, f inverse y is less than epsilon. We know f inverse y is x, so d of f inverse z, x is less than epsilon, or z is an element of v. That is, b rho y epsilon is subset or equal to v. That is, to each element y in v, there exists an open ball b rho y epsilon such that b rho y epsilon is subset or equal to v. This implies v is open with respect to the metric d, or v is an element of tau 1, or we conclude that tau is subset or equal to tau 1. That is the first result. And we have to prove that tau 1 is subset or equal to tau in the same way. On the other hand, consider v in tau 1 and let y in v. Then v is open with respect to the metric rho. Therefore, there exists epsilon greater than 0 such that b rho y epsilon is subset or equal to v. We claim that b d f inverse y epsilon is subset or equal to f inverse v. Take an element z, element of b d f inverse y epsilon, or d of f inverse y z is less than epsilon, or d of f inverse y f inverse f z is less than epsilon. That is, d of y f z is less than epsilon. This implies f z is an element of b rho y epsilon, which is subset or equal to v. That is, z is an element of f inverse v, or bd f inverse y epsilon is subset or equal to f inverse v. So we can write f inverse v as a union of such open balls. And bd f inverse y epsilon, where y is an element of v. This implies v is in tau, or tau 1 is subset or equal to tau. That is the second result. From 1 and 2, we conclude that tau equal to tau 1. Or we get the final result, that is why tau is metriceable. One more theorem, that is theorem is given statement that x2 and yu be topological spaces and let f from x to y. There are two parts to be proved. Part A, if f is continuous and sequence xn is a sequence in x and converges to small x, then the sequence f of xn converges to f of x. Part B, suppose x2 is first countable and for each x in x and each sequence xn such that xn converges to x, the sequence f of xn converges to f of x, then f is continuous. We can take the proof of it. Part A, suppose that f is continuous and sequence xn converges to x. We have to prove that sequence fxn converges to fx. For that, let v be a neighborhood of f of x. Since f is continuous, there exists a neighborhood u of x such that f of u is subset or equal to v. But sequence xn converges to x. That's what already given. Therefore, there exists, by definition, we know there exists capital N greater than or equal to 1 such that xn is an element of u for all n greater than or equal to n. This implies f of xn is in f of u for all n greater than or equal to n. This implies f of xn is in v for all n greater than or equal to n, because f of u is subset or equal to v. Hence, f of xn, that is sequence f of xn converges to f of x. That is what the first part, part A, or part A is proved. And coming to part B, suppose that x2 is first countable and for each x in x, sequence fxn converges to fx whenever sequence xn converges to x. Take let a subset or equal to x to prove that f is continuous. For that, it is sufficient to prove that f of a bar is subset or equal to f a bar. Last class we have studied a particular theorem. This part is that whenever f is continuous and a subset x, then f of a bar is subset or equal to f a bar. That we have proved last class. So for that, you take an element in f of a bar. Let y be an element of f of a bar, that is y equal to f of x for some x in a bar. This means there exists a sequence xn in capital A such that a sequence xn converges to x. Then by assumption, sequence fxn converges to f of x. Now, xn is an element of A. This implies f of xn is an element of f of A, but sequence fxn converges to f of x. This implies f of x is an element of fa closure. That is, y is an element of fa closure. This implies f of a closure is subset or equal to fa closure. It shows that f is continuous. And that's all about this particular section. And 7 pages notes I am giving. And go through this properly. And we can, any doubts means we can discuss in the class.